Assalamualaikum, dear student. This is lecture number 2 of week number 9. So we are continuing the chapter number 8, viscous flow in pipe. So the learning objective of this chapter we have discussed in the previous lecture. At the moment we are covering some part of this learning objective, which is identify and understanding various characteristics of the flow in the pipe. So some of the characteristics still to be discussed, and after that we will discuss the main properties of laminar and turbulent pipe flow and appreciate their differences. So we have discussed little bit the difference between laminar and turbulent. What exactly the laminar flow and turbulent flow, this we have discussed, but we will discuss little bit more in detail. Okay, so let's move on the topics we are going to cover today. The topics we are going to cover today are entrance region and entry length, comparison of laminar and turbulent flow, and after that we will discuss the pressure distribution along pipe, that is a straight pipe, and the pressure distribution along pipe, that is inclined pipe. So first we will cover these two topics at the top, and then we will move on to the number 3 and number 4. So now we are going to discuss the entrance region and entry length. What exactly it is, let's see and discuss. So the entrance region, so here you can see there is a reservoir which is connected with the diameter D of the pipe, and it is also connected with various fittings. This is basically elbow, two elbow of 90 degree are connected, and here it is another 45 degree elbow is connected with the pipe, and this is a reservoir. Okay, and there is a diameter of the pipe is D, which is connected with the reservoir. So here we are discussing the pipe flow, so that's why we have connected a pipe with the reservoir. So here we start. So let's see, any fluid flowing in a pipe had to enter the pipe at some location. Okay, so this is a reservoir and there is a pipe connected with the reservoir, and the fluid is entering to the pipe at this point. Okay, so consider a fluid entering a circular pipe, since we are using a circular pipe, at a uniform velocity. Okay, so here you can see the velocity is uniform. Okay, so your velocity at every point at the pipe is uniform. Okay, the region of flow near where the fluid enters the pipe is termed as the entry region or developing region. Okay, so here the fluid is started entering to the pipe, and at the entrance of the pipe the velocity of the fluid is uniform. So here we can I give you an example, because you see, whenever we have a large reservoir, okay, so just like you can consider the air velocity, okay, in the space. So we consider the every single particle of the air has a uniform velocity, is not different, is same like the fluid flowing in a river or in a sea, it has same velocity, it has a uniform velocity. Okay, so here this is a big reservoir. From the big reservoir, the velocity at the entrance we have a uniform, and now it's try to enter to a pipe. Okay, now it's entering a pipe. Okay, so after that what happens we will see. So the point or the region where it's entering, it's called a entrance region, or the region is also called a developing flow region. Okay, so when it enter to the pipe, then how the fluid flow changes, that we will observe. Okay, so let's move on to the next slide. So the fluid typically enters the pipe with a nearly uniform velocity profile at section 1. So here the velocity profile is uniform at the point 1. Okay, so as the fluid moves, okay, so this is a uniform velocity profile is indicating, okay. So as the fluid moves through the pipe, viscous effects causes it to stick to the pipe wall, no slip boundary condition. So as I told you before that earlier we used to discuss the ideal flow. In the case of ideal flow, throughout the pipe the velocity profile remain uniform, okay, it doesn't change because there is no viscous effect, there is no shear stress between the pipe, okay, and the fluid. But since we are discussing the viscous flow, so we have a viscous effect. Because of the viscous effect we have a shear force. So because of the shear force the velocity will not remain uniform throughout the pipe, so it will change because of the viscous effect. So how it happens, let's move on to the next slide. So here you can see the boundary layer in which viscous effects are important is produced along the pipe wall such that the initial velocity profile changes with distance along the pipe X, okay. So here you can see this line, this dotted line, can you see that? This dotted line where I move my cursor, okay. So this line is called the boundary layer line, okay. This line is called line of boundary layer, and this boundary layer is due to the viscous effect. Here the viscous effect is maximum at this point because the velocity is 0, okay. For no slip condition, I explained to you before, for the no slip condition the viscous effect is maximum at this point and the velocity is 0, okay. So as the fluid moves forward in the pipe, so what happens, the viscous effect started decreasing, okay. The viscous effect started decreasing, and because of that what happens, the velocity profile changes. Here you see the velocity is uniform, but at this point you see because of this shear force, because of this shearing effect, okay, the velocity gradually increases, okay. At the bottom velocity is 0, but as you move forward the velocity gradually increases, okay. So when I move further forward, what happens, velocity is further increases. So let's understand this point. Here initial velocity profile changes with distance along the pipe X. So as you move forward along the x-axis, what happens, the velocity profile changes from uniform to some other profile, okay. So that means in this portion the velocity is changes along the x-axis and along the radial axis. You can see if you go along the radial axis, here along the x-axis and the radial axis the velocity is not changing, okay, in this case. But here you can see the velocity is changing along the x-axis and as well as the radial axis. Here the radial axis, at this radius velocity is different, at this radius velocity is different, okay. So until the fluid reaches to end of the entrance length section 2. So this is the end of the entrance length. You can see here from here to here is called entrance length. So why the entrance length is ending here? Because beyond which the velocity profile does not vary with the x-axis. After this point, okay, where the shear stress become 0 at this point, okay. So at this point the shear stress is 0, okay. So at this point the velocity profile does not vary, velocity does not change with respect to x-axis. If you go further, velocity profile will not change, velocity profile will remain same. So this point is called where we get the proper velocity profile of the fluid that point is called the end of the entrance region. Okay, so here you can see from both the end. Okay, so this boundary layer is basically the layer where the viscous effect is dominant. Okay, and with this is the region that is called inviscid core. Inviscid, you understand, it means the fluid is not viscous. So this is basically called a inviscid core. Okay, and this line is called boundary layer, which is formed due to the viscous effect. Okay, here you can see the yellow portion. This yellow I indicated. So this is basically the region of viscous effect. Here the fluid is viscous. Okay, and this line is called a boundary layer line. Okay, so the boundary layer has grown thickness to completely fill the pipe. So here you see initially the boundary layer line is thin. Okay, with respect to the boundary of the pipe. So as it moves forward, you see the boundary layer is growing thick. Okay, it's going thick till it's completely filled the pipe. So till here it is completely filled the pipe. It's coming from here, it is coming from here. Now it is completely filled the pipe. Okay, so this line is called the boundary layer line. Let's move on to the next slide. So viscous effects are of considerable importance within the boundary layer. Okay, outside the boundary layer the viscous effects are negligible. So because you see this is the boundary layer, okay, and this region is outside the boundary layer. So here the viscous effect is negligible and this region is called inviscid core. Okay, so here the shape of the velocity profile in the pipe depends on whether the flow is laminar or turbulent. Okay, the shape we are seeing here after the entrance region or developing region. Okay, this region is called fully developed region. So in the fully developed region, the shape of the velocity profile is depending on whether the flow is laminar and turbulent. And how we can determine whether the flow is laminar and turbulent? It depends upon the Reynolds number. If the Reynolds number for a pipe, okay, as the geometry changes, the limit of the Reynolds number changes for the laminar flow and the turbulent flow. So if the Reynolds number is less than 2300, that means flow is laminar, and if the Reynolds number is greater than 4400, that means the flow is turbulent. And if the flow is laminar, we can find out the entrance length. Okay, how long is the length, after what length the flow would be completely fully developed. So that we can find out by using this formula if the flow is laminar. If the developing flow is turbulent, so we can determine the entrance length by using this formula. Okay, and we can get the entrance length. So you can see this, the importance of this inviscid core is also very, very important. Okay, so consider if you have a case, you have a wind tunnel and you want to test a car in a wind tunnel. So normally you see we don't drive a car in a tunnel or somewhere. We drive a car in an open atmosphere. In the open atmosphere, we consider the flow is uniform. Okay, the flow is uniform, and you see in a flow is uniform. So we have a proper dimension of the car. Okay, so if the flow, so if you want to test, test a car, so how would you test that? You need an environment of uniform flow. Okay, so where you can get the region of uniform flow? The region of uniform flow is this, the inviscid core. So this is the inviscid core. So you have to know what is the length of the car, what is your length of the car, and how big supposed to be the inviscid core. okay, so that you can bring your car within this region to test your car, okay, because only in this region you are getting a uniform flow. So your wind tunnel must be designed in such a way that you can get in viscid core, okay, long enough to bring your car within this core, okay. And also you should know what is the width of the core. So you know the width of your car, and based on that you must know what should be the width of the core to test the car, and what should be the diameter of the pipe to achieve that width of the core and length of the in-viscid core to test the car. So this is a very important application of the in-viscid core that you must keep in your mind, okay. How we can calculate the length of the in-viscid core? By using this, you can calculate that. If you know the length of the core, you can calculate the diameter of the pipe to test the to get the width of the in-viscid core. So this is the formula, okay. So now let's move on to the next slide. So once the fluid reaches the end of the entrance region, the section 2, this is the section 2, the fluid is simpler to describe because the velocity is a function of only the distance from the pipe center line R and the independent of x. So here, after reaching this region, the velocity profile is no longer is the function of x, it is the function of radius only. So now after point 2, the flow is simpler to describe because the velocity is the function of only the distance from the pipe center line R and independent of x. So here you can see only the velocity is varying in the radial direction, but throughout the length this profile remain constant, okay, it is not going to change. So there is no variation. So del V by del X is going to be 0. Yeah, del U by del X, because the velocity component in x direction is del U by del X is 0, okay, because there is no change this. But up from this point to this point, velocity profile is continuously changing in x direction, okay. So velocity profile is continuously changing up to the point 2, and at this point this is the end of the developing region or entrance region, and this is the startup of the fully developed region. So the flow between 2 and 3, which is the fully developed region, is termed fully developed region or fully developed flow, okay. So this is another picture. Here you can see this is the entrance region, and velocity is starting from uniform flow, okay, and then it's gradually changing up to it's reaching to the entrance region, okay. This is also called a hydrodynamic entrance region. This is called entrance region, this is called hydrodynamic entrance region, because dynamics of the fluid is continuously changing, okay. But at this point, one thing is very important to know, that the average velocity at every single point is same, okay, since the diameter is not varying. Second, the velocity we have only one dimensional flow, not the one dimensional flow, the velocity we have only one inlet and one outlet, and area is not changing. So that's why at every point, whatever is the velocity profile, the average velocity will same, okay. Even after the fully developed region, the velocity profile will be same. So up to the hydrodynamic entrance region or developing region, the velocity is a function of r and x, okay, and at that point the change in velocity with respect to x is not equals to 0. But as soon as you reaches to the developing region, so the change in velocity with respect to x-axis becomes 0, and velocity is only the function of radius, okay. And how the boundary layer thickness? So this is the boundary layer. You can see this line, and this line is developing only because of the viscous effect, since the viscous effect at this point is maximum. Okay, at this point the viscous effect is maximum. So as we are moving forward to the pipe, the velocity effects, it's gradually decreasing. At this point here the velocity effect is 0. At this point, at this point the viscous effect is 0. 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 Okay, so wherever the viscous effect ends, it becomes uniform, the velocity becomes uniform, right? So as the viscous effects varies, the velocity profile changes. The velocity profile changes. The velocity profile changes. Okay, till we get the final fully developed velocity profile. Okay, so this line is called the boundary layer due to the viscous effect. Okay, so now let's move on to some important notes about the entrance region. The velocity profile in the fully developed region is parabolic. Okay, because this is, you can see the parabolic shape in the fully developed region. Okay, in laminar flow or somewhat flatter or fuller in turbulent flow. So in the fully developed flow, the profile might could be laminar or could be turbulent. Okay, if it is laminar, so it's going to be parabolic. If it is turbulent, so it's going to be little bit flatter like this, flatter like this. It will be flatter like this. Okay, in that case the velocity normally become more uniform. Okay, so when the velocity profile we move into the developing region, the flow will be either laminar or turbulent. Okay, so the time average velocity profile, okay, remains unchanged. Okay, when the flow is fully developed and thus u is a function of r only. Okay, the time velocity profile remains unchanged. Okay, because in the x direction in the fully developed region there is no change in velocity, only the change in velocity with respect to radius. Okay, so the velocity profile remains unchanged in the fully developed region, so does the wall shear stress. Okay, so after that the shear stress also remain constant, because if the velocity is not changing, that means the shear stress will also not change, it will also be constant. Understood? Okay, the wall shear stress is the highest at the pipe inlet, where the thickness of the boundary layer is smallest. As I explained to you earlier, here is the thickness of the boundary layer is smallest, the shear stress is maximum, and decreases gradually to the fully developed value. Therefore the pressure drop is higher in the entrance region of the pipe. Okay, so here the pressure drop, we will talk about later. Here the pressure drop will be higher, we will talk about little later on the pressure drop. Okay, so entry length, we little bit more important points to be discussed. The hydrodynamic entry length is usually taken to be the distance from the pipe entrance to where the wall shear stress and thus the friction factor reaches within about 2% of the fully developed flow. Okay, so this we have already discussed. The laminar flow, the hydrodynamic entry length is given approximately entrance length, developing flow region. Okay, or hydrodynamic entry length is same, is given approximately. This is the formula that we can use it if, okay, if the flow is laminar. In turbulent flow, the hydrodynamic entry length for the turbulent flow can be approximated by using this formula. Okay, the formula we have discussed before and the formula we are discussing here is the same. The entry length is much shorter in turbulent flow as expected, and its dependence on the Reynolds number is weaker. Okay, so in the case of turbulent flow, the entrance length will be smaller. Okay, if the Reynolds number is weaker, if the Reynolds number is just close to the 4400. Okay, in the limiting laminar case, okay, if the flow is laminar and Reynolds number is 2300, the hydrodynamic entry length is 150 diameter. So whatever is the diameter, the value of the entrance length will not increase more than 115D. Okay. In many pipe flows of practical engineering interest, the entrance effect of the turbulent flow become insignificant beyond a pipe length of 10 diameter, and the hydrodynamic entry length is approximately is equals to 10 diameter. That means the importance of entry length after 10 diameter in the turbulent flow is insignificant. Okay, so if the flow is turbulent, so after 10 diameter of the pipe we can install any proper measuring instrument, considering that the flow is fully developed. So that's why we are not worried about that once if the flow is turbulent. And if we have a straight pipe up to 10 diameter of the pipe, so we can install any equipment and we consider the flow is fully developed in entrance region is end. Okay, the irregularities of the flow is over. So in turbulent flow it is reasonable to assume the flow is fully developed for a pipe whose length is several times longer than the length of its entrance region. So if we are seeing the length of the pipe is longer than 10 diameter, so we can assume that the flow is fully developed. Okay, so now we are going to further comparing between the laminar and turbulent flow. Okay, so what is the main key points which differentiate these two flow? Okay, so there are some major differences between laminar and turbulent fully developed flow in pipe. Okay, so here we are talking about the fully developed flow. In the case of fully developed flow, okay, if the laminar flow in case of fully developed flow and turbulent flow in case of fully developed flow or in fully developed region. So laminar flow, how we observe in the fully developed region, can solve exactly. So if whatever is the problem, we can solve or we can get exact solution for this. Okay, or we can solve very easily. And we have equations available to handle such cases. Okay, the flow is steady. In that case the flow is steady. Velocity profile is parabolic. And pipe roughness not important. In that case the pipe roughness doesn't give a much effect on the fluid flow. Okay, it turns out the V average is equals to half of the U maximum, because you see this is the maximum velocity, because this is the magnitude of the maximum velocity profile. So this is the maximum velocity at this point. Okay, so V average is half of the maximum velocity. That means this is half of the maximum velocity, it is indicating here. And U is equals to function of 2 average 1 minus r square over r square. So it is indicating that the velocity profile is a parabolic, is a second degree equation. So here you can see the velocity profile is parabolic, and mathematically we will prove in the later part of the lecture. And in the turbulent flow we can see the flow is like that, it is more flatter. Okay, but at every instant the velocity profile is different. Okay, it is not in a proper shape, so we take this profile as an average. So now we can see cannot solve exactly too complex because the profile is not constant, so we don't know the exact profile of the turbulent flow. So we do not have a proper solution for this and proper equation to apply, so it is not easy to handle. Okay, flow is constantly 3D swirling eddies, but it is steady in the mean. Okay, you can see this the eddies. Okay, the irregular every instant the velocity profile is different, it's not same. Okay, its behavior is 3-dimensional, but the average is same. This is the average line of the profile of the all velocity profile at every instant. So mean velocity profile is fuller shape, more like a top hat profile, with very sharp slope at the wall. Okay, so this profile is very close to the uniform velocity profile. So pipe roughness is very important. In that case the pipe roughness is very important, okay, because the pressure drop is very higher. So vary 85% of U max depends on Reynolds number a bit, okay, so it varies, okay. So here the velocity, the average velocity is 85% of the U max. So this is the U max. The average velocity will become 85% of the U max, okay. No analytical solution, but there are some good semi empirical expression that approximate the velocity profile shape, okay. So here are the big differences between the velocity profile and the laminar and turbulent flow, and I discuss about the entrance length. So rest of the lecture I will discuss in the later part of the lecture, okay. So this is the end of the lecture.